So seems like it ran. Let me dig out the plot, and you can see we've got something that looks approximately like exponential decay, but it's actually hit 0 without flattening out. So if I know this is actually exponential decay, I expect it to hit 0 being almost flat. So I'm a bit suspicious of this graph. K1 times VA, so that looks right. Let's try and reduce the step size and see if that makes it more like the exponential decay I expect. Okay, so again, what happens if you use this simple way to plot something? You need to close the existing one. So one way to close any existing ones is to call this command at the start. So it hasn't changed. It falls very sharply. Levels off, so not quite sure what's going on there. Quarter T, append T. T equals time start, that looks okay. T equals T plus step time. Let's just check what B looks like. So run. So this is why I was made a mistake. I can see that my axes are the wrong way around on my graph. Of course, I plot the X one first, then the Y variable. Okay. So now I get what I expect. So as it's emptying, it's showing exponential decay. Right. So I can actually plot all of them now if I wanted to. But at this point, now I've got my code working, this is where I might actually modify this to be a bit more, so I can actually work with my plot a bit more easily. So create a figure and properly modify it. So you can see we've got A, B, maybe I should add legends. So label equals A, label equals B, C, D, plot.legend. There we go. So A is blue, so it empties out of A, B comes like this, C goes like that, and then D fills up and eventually finishes at the same value that A started at. And at any time, it should be that the volume in A, B, C, and D adds up to 1. So if I wanted to, I might create a set, record like the sum of the volumes in each one. And for instance, if your algorithm is working correctly, that is going to stay conserved. If your algorithm, for whatever reason, was causing you some problems, you might see that this conserved quantity isn't conserved anymore. But it depends on how you've set your equations up. So I think in this case, even an error in my, even if I was getting inaccuracies, I think it would still add up to 1. Right, so I'm happy here. I've got my graph. If I review my code, what I'm thinking of, if I see the same sort of bits of code multiple times, then I start thinking, is that the most efficient way to do it? So let's tidy up by assigning all these things the same way. You can see here this is seems a bit messy, but I'm going to leave that. So here I could do it like I've done here. Tidy this line up, so assign them all at once on one line, so keeps my code a bit more compact. Then actually you can see that I read the next step from here, I save them, and then I replace the current. I can actually just load the results straight into the current values here. So just tidying up that. And I can delete that. And furthermore, I can copy this bit of code here, just put it here. Once, instead of assigning the 0 values, I can set my current values to be those and then load them in. Then perhaps depending on how you could do it, you could rearrange this so you only you don't have this sort of duplication here, but I'm going to leave that in. It's not too much of a worry to me. Right, check that all those changes haven't ruined my file. Run. No, it's still working as I expect, so tidied it up a tiny bit, and there's my model. So for instance, I could change my model so that now the water flows out of D, so K4 equals 0.01. We've got a flow out of D, which is K4 times VD. So now, instead of all accumulating in D, because I've changed the rate of D to, I've effectively opened the plug hole on D. Let's just run that and see what happens. See, now D rises and then empties out. But it's still, so if you look, the first one had a maximum level of, or a maximum volume of 1 litre. This one had a maximum volume of sort of 0.35 of a litre. This one maybe 0.25, this one a bit lower. So it hits the maximum and then declines. Okay. So, or I could leave that in and say, what happens if I have a constant flow into A? So let's call that K0. And the constant flow could be, let's say, K0. Let's keep it constant, 0.01. So now I have a constant flow into the top bathtub. The bottom bathtub has its plug hole opened. What's going to happen over time? So run it. Let's see. So if you like now, you can see for a start what's happened to my blue line. But if you can't see a line on the graph, Python automatically scales the graph so it should fit your data. So if you can't see it, it means it's either below, exactly on top of one of these lines, or exactly below one of the axes. So in this thing, thinking about it, what I said was, look, K0 is 0.01, so 1% of the volume flows in all the time. But as I also set my rate out of the RA to be K1 times VA, and VA starts as being 1, right at the start these are balanced. So the volume of A is constant, but I need to change the axes to see that. And to do that, I need to start with a figure, so fig.add subplot 1 1 1, so just one plot on my figure, and that's going to give me an axis when I create the subplot. Then it's this axis that I'm going to use to plot everything on. That's the figure I'm going to be showing. And also, so ax.set x limit 0 to 1.1. I've remembered what that command should be. Plot.figure. Of course, I need to assign that fig equals no set limit. So let's have a look at my something where I've done this before. Set ylim, that's what it's called. Let's close that. Set y limit, not the x limit. So now you see, because I draw it to 1.1, I can see this line. So it turned out I picked a sort of an odd situation. In general, let's have a lower flow rate into A and see what happens. So I've just left my tap dripping with all the plugs out. See, now the water flows out of A until the volume is reduced such that the flow in is balanced by the flow out, and all the other baths also eventually reach the same level. You can see this blue line hasn't quite definitely reached a stable sort of a flat line indicating nothing more is going to happen, so I might increase my time period. I'm going to simulate that over. So I think from the look of it, by about another 500 should do that. Okay, so now I can see my system's reached a steady state, and the steady state when you've got the top tap dripping in is that all the bathtubs will have the same level, such that the drip into A drips through into B, so you like there's a constant rate flow between all the baths in the system and the levels stay empty. So that's what we call a dynamic equilibrium. So there's some flow into and out of A and B and C and D, but the overall level stays equal because the rates are all balanced.